The Galaxy Mission Lab from St. Columba College and the Seirei Christopher High School are honored to be here today to share our project, Biosolutions for Space, Bricks and Bytes. We would like to acknowledge the invaluable support we have received from Connecting Minds, Dr. Leek van der Hulst from the Adelaide University, David Hawksley, La Trobe University, and Daniel Williams at the UniSA Materials Test Lab. We are grateful to the Andy Thomas Space Foundation for making our research possible.
Our team explored ways to use the cradle-to-cradle design principle to support life on Mars. Long-term missions need more than resupply from Earth. They need to establish sustainable, consistent bioproduction systems in situ. We discovered that mushrooms could supply an expanded range of nutrients and improve the menu. They also had potential to be used in the production of composite materials to use for building and radiation shielding.
Our team communicated by Zoom calls, emails, and shared PowerPoint presentations. We shared our research, resources, and experiment across 3 linked Padlets. Padlet is like a giant shared pinboard in a file storage platform. With it, we could brainstorm, add our research, and share ideas and images quickly and very easily. We also learned together, completing the online workshop Operation Eyes on Earth with the Australian Space Discovery Centre. We connected 2 growth tents to create a DWC plant growth chamber and a dark humidity-controlled tent for mushroom growth. The mushroom serves dual roles, as a supplementary food source and as a producer of mycelium for further brick manufacturing. The corn and later beans provided food, as well as a mushroom medium and seed for future crop.
Our experiments cultivating oyster and Australia mushrooms, reishi and turkeytail on hemp herd, corn waste and sugarcane mulch found there were distinct substrate preferences, with oyster thriving on corn and reishi on sugarcane. Waste from our corn crop was chopped and pasteurized to provide a sterile substrate for mycelium growth. After a week of growth, we pressed the mycelium into a brick form mold, and after another week of growth, the bricks were removed from the form and dried in a warm oven for 2 days.
Together, these systems form an interlinked cycle where agricultural outputs support material productions and structural materials contribute to habitat resilience through radiation shielding. This biological technical loop exemplifies the C2C approach, moving beyond resource efficiency to regenerative design.
Laboratory testing of our mycelium composites demonstrated measurable flexural strength across specimens of varying thickness from 9.3 to 11.8 millimeters, indicating good potential for making lightweight, insulating building blocks when combined with the regolith fill.
The hemp herd block showed moderate bending resistance. The corn block was considerably weaker. This inconsistency could be due to poor material uniformity or manufacturing defects. The corn mycelium brick was clearly less dense and not uniform in composition. This was due to the rough chopping in the preparation process, and ongoing testing will need to optimize particle size to mycelium growth. The compressive load of regolith on the brick is orders of magnitude lower than yield capacity, so the brick should easily support self-weight and stacking, provided load is evenly distributed.
One of our primary goals was to provide radiation shielding for Mars habitats. NASA has invented considerable research funding to using mushrooms for radiation screening and as a renewable building material. We used the Phi Lab's online nuclear test laboratory to determine background radiation readings and compare them to a range of common material shields. Our mycelium composite will be tested at Phi Labs to confirm their shielding properties.
As always, we wanted to multiply our output, so our Japanese teammates developed jerky bites, which could also provide a growth medium for the mushrooms. As a food source, jerky bites can promote relaxation through both its texture and its ingredients. Chewing helps calm nerves, reduce stress, and boost serotonin through rhythmic motion. Functional ingredients like CBD may reduce anxiety, improve sleep, and relieve pain.
Our aim was to create a jerky-like snack by juicing vegetables and fruits, adding gelatin, then drying them to make jerky bites. To achieve this, we researched existing jerky and gummy products for texture and shelf life. We also experimented to find the ideal shape. For example, our initial tube shape was replaced with a new gummy-based shape due to technical challenges. Multiple prototypes and regular discussions helped overcome challenges and produce a practical product. To begin development, we gathered a range of fresh foods and carefully weighed them.
We experimented with different ratios of pureed fruits and vegetables mixed it with gelatin to develop green and orange jerkies. A yellow blend with bananas was unsuccessful as it did not set due to the protein digesting enzyme in bananas. Breaking down the protein in gelatin, we researched with nutrients. We also experimented with dry time and method to refine the process.
We perfected our recipes and shared them with our Australian teammates. They tried to duplicate our recipes and test which is best suited for mushroom germination. Next, we experiment with creating mushroom jerky and adding herbs and spices to increase food variety. A further area for research is creating jerky for mushroom cultivation from waste greens. Shelf life and packaging optimization will also be explored. What we realized during this project is that food isn't just about nutrition. It also plays an important role in supporting health and even psychological well-being, something especially important in space mission. To address this, we developed a snack that combines both nutritional and functional ingredients. The process wasn't easy. We faced the formulation and structural challenges, but through iteration and teamwork, we are able to overcome them. In the end, this experience showed us that even small food innovations can have a big impact, not only for space exploration, but also for everyday life.
Establishing sustainable settlements on Mars requires regenerative links between food, construction, and waste. Guided by cradle-to-cradle design, we paired mycelium bricks with a cone-beam hydroponic system. Mycelium composite shows strong right-way insulation and when filled with regolith, provided NASA-level radiation shielding. Corn grew well with beans through nitrogen fixation, while corn grew mushrooms that supplied both food and brick material. Next steps include spore collection and optimizing crop growth. In Japan, we developed fruits and vegetable jerky, a compact food that boosts serotonin and doubles as a mushroom medium. Together, this integrated system demonstrates how nothing is wasted. Each byproduct supports a food infrastructure and long-term life on Mars. Thank you for listening.